Welcome to Chapter 10. We'll discuss networks and telecommunications. We'll describe networking principles and some security mechanisms. We'll touch on the OSI reference model and its security lapses, physical and logical network topologies, TCP/IP and how it works, network security risks and defense tools, and wireless networks and security controls. So the Open System Interconnection OSI reference model. This is a really good model that helps most people learn about how our networking is designed and works. But the biggest part is we broke it up into layers to help developers and hardware manufacturers focus on certain layers that they were responsible for, and if they met the requirements at each layer, that they were responsible for, they didn't have to worry about the other layers because that could be somebody else's job to deal with. But so we have a 7-layer model from the OSI model. A lot of this has also been simplified down into a TCP/IP model. We may talk about that a little bit too. But the OSI model is a 7-layer model, and it has the application layer. That's the user interface. That's where the web browser or whatever the actual user is utilizing. That's the application layer. Email software. Even a game, something like Solitaire, if it's networking. If it's dealing with networking, it could be a network app. Words with friends, things like that. Those are applications, the application layer. Presentation layer is responsible for the coding of the data. Sometimes it can also do encryption. Generally takes place in this layer, but it's presentation of the data formatting, encryption can occur here at layer 6. Session layer. This layer is responsible for maintaining the communication sessions between computers or devices. The session layer creates, maintains, and disconnects communications that take place between processes over a network. And this is layer 5, the session layer. The transport layer, layer 4. This layer is responsible for breaking data into packets and properly transmitting it over the network. It offers flow control, and error checking can take place at the transport layer. This is where you have TCP works at this layer of the TCP/IP. This, the transport layer protocol is TCP. There's also UDP that gets used quite a bit as well, but they both work at the transport layer, layer 4. Network layer, layer 3. This layer is responsible for the logical implementation of the network. And one very important feature of the network layer covered later in this chapter is local addressing. The TCP/IP networking model, this is the IP section, and the familiar with like the IP addresses. This is also where your routing occurs. Layer 3, your routers are said to be a layer 3 device, and they deal with the routing. They deal with IP addresses and IP, because this is the part of the IP part of TCP/IP is at layer 3. Layer 2 is our data link layer, and it's responsible for transmitting information on computers connected to the same local area network or LAN. The data link layer uses the media access control or MAC address to identify the devices, and device manufacturers assign each hardware device a unique MAC address. That's burnt into the network cards so that no one computer would have another duplicate MAC address. First half of the MAC address identifies the manufacturer, the other half identifies the actual physical card. Data link layer, layer 2, this is also where your switches typically work. Switches are typically a layer 2 device. and they deal with MAC addresses, whereas routers, they're a layer 3 device, and they deal with IP addresses. The last layer, layer 1, is the physical layer. This layer is responsible for the physical operations of the network, and the physical layer must translate the binary ones and zeros of computer language into the language of the transport medium. In the case of copper network cables, it must translate computer data into electrical pulses. In the case of fiber optics, it translates the data into bursts of light. We have two main types of networks: a wide area network, and it connects systems over a very large geographic area, and then local area networks, and they provide network connectivity for those devices located in the same geographic area, or even typically a building even. Wide area networks, the internet is an open network, can't guarantee privacies, and considers the security issues surrounding the use of an open network. So consider the use of security issues surrounding the use of an open network. And you could develop your own private WAN using dedicated lines versus traversing over the internet. But in a lot of times now, a lot of organizations will use site-to-site VPNs, or virtual private networks, to create their WANs. So WAN connectivity options: you have cable modems, DSL, fiber optics, satellite dial-up, cellular, 3, 4Gs, 5G networks. You also have T1s, T3s, things of those natures, and SONET networks. You can also deal with those, the OC levels, for larger organizations. But in a lot of cases, fiber optics is probably going to be used for businesses. Okay, router placements. So you have border routers. A border router is subject to a direct attack from the outside source. When you configure any router, you should determine whether it's only point of defense, or if it's the only point of defense, or if it's part of a multi-layered defense. Of course, a multi-layered defense is far better and more secure. The lone defense router can protect internal resources, but is subject to attack itself. And so here in this instance here, you have that border router behind the firewall. In some organizations, it's in front of the firewall. It's probably better to have it behind the firewall, but it's personal choice sometimes. But it does need to be. You do need to have the router. But most likely it's probably going to be in front of the firewall. The internal router, now this can provide enhanced features for your internal networks and help keep the subnet traffic separate, and keep traffic out of a subnet and keep traffic in a subnet. For example, an internal router that sits between the network of an organization's research department and the network for the rest of the organization can keep the two networks separate. These routers can keep confidential traffic inside the research department, and they can also keep non-research traffic from crossing over into the research network from the organization's other networks. And in a lot of cases, you'll have another firewall. A lot of times you'll have firewalls back to back, and you'll have that server off the border router. That'll be in the DMZ. And that'll be between the two firewalls. So I don't like this image as much. I mean, it is a configuration that a lot of organizations use, but I've also been in most organizations that I've been in will use a double firewall, having another firewall between the interior router and the border router. And you have two firewalls leading in between the server, the DMZs. So But this does work. It is effective. At least it does have a firewall, and it does have two routers: an internal router and an external router. Local area networks, or LANs. Systems on the same LAN do not protect themselves from each other, so good security is important, right? So you need to have them patched and updated, because the idea of a LAN is that they're interconnected and be able to reach each other for the most part. Switches are fairly open, but you can create virtual networks or virtual LANs, and use the router to segment and hide certain computers. But those computers on the same LAN have access to each other for the most part. You can implement some firewalls and some other devices to secure it down, but generally devices on the same LAN have access to one another. That's usually the goal. Ethernet networks. Ethernet is the typical standard that every company will use today. It defines the way the computers communicate on the network and governs both the physical and data link layers, and defines how computers use MAC addresses to communicate with each other on the network, and it has become the most common LAN technology in use. LAN devices. So most likely you will never see a hub. I haven't seen one in a very, very long time, decades. But they still do exist, I guess. But mostly you'll see switches. But the main difference between a hub and a switch, the signal comes in on a hub and it goes out all ports on the hub. It doesn't do any switching or thinking or checking or anything. It just, if a signal comes in on one port, it sends it out the other ports, all other ports. Switches, though, they look at it and try to determine which port it needs to go out of. So if you had a 24-port switch, which is typical, if it comes in on port 3, it tries to figure out by MAC address where the destination of that packet is going. It figures out, that's the MAC address that I've seen coming off of port 15, and so then it sends it off port 15 and only port 15. So it saves your network, and you have a lot more bandwidth available for your network because you're not flooding the whole network all the time with every single packet. It's more logical, it's more intelligent than a hub. Virtual LANs, right? So these are basically logical networks that you create on your switches, and they need to be a managed switch, a more intelligent switch, because you have some basic home switches that don't have the capability of doing virtual LANs, but with a more robust switch, you could do virtual LANs, and you can basically, on a 24-port switch, you could have probably up to 23 different networks on there. You would need one port that would be able to talk and trunk all those out. But you could technically have 23 separate networks on a 24-port switch, and none of those ports could talk to each other except for with going to the router and then coming back. So VLANs, they create broadcast domains, and so they isolate each other from other networks, and that's why you need a router. To communicate between two different LANs, you need a router. Even if they're on the same switch, if you have virtual LANs, you need a router to communicate between two different LANs. A VLAN is just a collection of logically related network devices that are viewed as a partition or network segment that is different from the other networks on that switch. And it's used to isolate logical groups of devices to reduce network traffic and to increase security. Once again, like if you had a research area and you wanted to keep things isolated to that research area, you could create a virtual LAN and say maybe you gave them the first 10 ports on the switch, and they could all talk to each other and be fine, but they couldn't talk to any of the other devices on the other ports of the switch, and you wouldn't have impacts and things like that that could be caused by broadcast storms or things that the research department was doing. TCP, IP, it's a suite of protocols that operate at both the network and transport layers, right? TCP works at the transport layer 4, and IP works at the layer 3, the network layer of the OSI model. It governs all activity across the internet and through most corporate and home networks. It's basically the protocol of choice and standard. It was developed, though, by the DoD to provide a highly reliable and fault-tolerant network infrastructure, but sadly, security was not a focus and security was not built in. Here is the TCP/IP protocol suite. Right? You have various different protocols at the application level: FTP, Telnet, HTTP, SMTP for email, DNS, domain name service, SNMP, simple network management protocol, DHCP, and then NST. And so you have TCP, which is a error correcting and connection oriented protocol, and you have UDP, which is a connectionless oriented protocol. So UDP just sends and forgets; it doesn't care. TCP sends and monitors and makes sure all the packets arrive, and then of course they send down to the IP layer, network layer, and then the data link layer and the physical layer. IP addressing. So we have two versions. IP version 4 addresses. You'll find these mostly anymore. You'll find them as internal addresses. We pretty much ran out of IPv4 addresses. There, a lot of organizations still utilize them, and especially internally, just because they're much easier for us to deal with. You can see the example number there, 192.168.10.1 is an example IPv4. It's a 4-byte, 32-bit address that can uniquely identify every device on the network, and it is still the most common, especially for internal network addresses. We're moving more and more towards IPv6 addresses. It's been a long time coming and a lot of pushback, but we ran out of IP4 addresses, and so it's going to get to be the point where we have to use the IPv6 addresses, at least externally and on the web, with all the mobile devices and everything that we have. It's just getting to be needed. And they are 128-bit long, so they're 4 times as many bits, but there is just an exponential amount more IP addresses, and they do provide more unique device addresses, and the IPv6 is more secure. It has some security built into it as well. DHCP is used within a network to simplify the configuration of each user's computer so that you don't have to manually enter in an IP address, and you can do IPv6 addresses or IPv4 or both. You can do what is called a dual stack. You have common ports. Any port under 1024 is the well-known port addresses. And here are some example ports and the services that use them, such as 22 is a secure shell, 53 DNS, 80 is web traffic, HTTP, 443 is SSL. And here it's just giving some more of the common port numbers, with the secure FTP of 989. So FTP secure, so it's FTP over TLS SSL, because normally FTP is in the clear. So if you want it more secure, you would use the FTPS. And here's some even more protocols and their ports. So, and then you have a different type of file transfer. The secure FTP protocol is SFTP, and it uses port 22 just like SSH and secure copy, which is also part of SSH. And SSH is the secure shell and operates on port 22. All right, Internet Control Message Protocol, ICMP. It's a management and control protocol for IP. It delivers messages between hosts about the health of the network. One of the more common one is a ping. A ping sends a signal packet to a target IP address, and really a ping is an ICMP echo request, and then it gets the echo reply, and so that allows you to ping a device and see if it's available on the network. Traceroute also uses the ICMP echo request packets to identify the path that the packet travels through a network, and it tries to indicate how many routers that it's gone through. But a lot of times most routers are set to not respond, and so you don't get a lot of very valuable information as much anymore. But it is available, and it's sometimes useful. Network security risk. Reconnaissance, the act of gathering information about a network for use in a future attack. So they could be, checking your trash, trying to see what you've got, what kind of hardware, all kinds of things, beyond just checking out your building. And who knows? There's all kinds of ways of doing reconnaissance. Eavesdropping, when an attacker taps the data cable to see all data passing through it. Denial of service is just flooding the network with traffic, or a device with traffic and shutting it down so that it's not usable by users because it's overwhelmed. Distributed DOS just uses multiple compromised systems to flood a network instead of a single device, so it's a distributed attack. And then a telephone denial of service attempts to prevent telephone calls from being successfully initiated or received by some person or organization. It's kind of an old hack. Basic network security defense tools. You have firewalls, virtual private networks and remote access, network access control, or NAC. Firewalls control the flows of traffic by preventing unauthorized network traffic from entering or leaving a particular portion of the network, and they can be very robust and be at a layer 2, 3, 4, or even higher. They can go up to layer 7. They can actually inspect the actual packet and make decisions based on what's in the application, as far as what's even on the screen. If you have a social security number or something like that, it can, the firewall can actually reach down into the packet and mask and hide or even remove a social security number or something like that. I mean, they can be very sophisticated. They could not just block network traffic. They can actually change the traffic itself. So some security features of the firewalls: flood guards and rules can limit traffic bandwidth from hosts, reducing the ability for any one host to flood a network or create a denial of service. Loop protection: firewalls can look at messages, addresses to determine whether a message is being sent around an unending loop, for example, from another form of flooding. And network separations: they filter rules enforcing division between networks, keeping traffic from moving from one network to another. At the base level, a firewall is a router with just added security features on it. And there are several types. The packet filtering, it's the most well-known, the earliest type. It just blocked based on network addresses. If it came from this IP, it's allowed. If it came from this IP, other IP, it's not allowed. That kind of filtering. Stateful inspection, that is allowing it to help understand and be aware of what's going on, and it can also keep sessions. So if you already established a session, you might get a less thorough inspection on the packet because it's already an existing connection. And also in the packet filtering, you have to have two rules, one in and one out for a connection, whereas in stateful inspection, it can keep state, and you only need one rule, and because it remembers that you let one in, so it has to let one out, or if you let one out, it has to let one in. So that's a stateful inspection. Then the application proxy, the application firewall type firewalls, like I say, they can work at the application layer, and you can actually manipulate the data or really reach into the data and look at the data and block it based on the data and the actual contents of the packet. All right. Deployment techniques. You have border firewalls, which is typical. You should at least have a border firewall. Screen subnets or DMZ firewalls, as I mentioned earlier. In a lot of cases, you should have two firewalls: a border firewall and then the internal firewall, and so that basically creates a screen subnet or DMZ between the firewalls. And also like the multi-layered firewalls. You want to create layers in defense. Here's the border firewall. As I said, typically the router outside the firewall and the firewall blocking the internal network. But in a lot of cases you'll have an internal router though on the other end. Here's the screen subnet, where the DMZ is off the firewall, and the network is off the firewall, and they don't show the multi-layer, of course. The multi-layer would have one more firewall in front of the LAN, in front of that switch, and then, like I said, you probably would even have a router in between the switch and the second firewall, but that would be your multi-layer. Unified Threat Management, UTM, it tries to unify all your threat management. So URL filters to help you filter web traffic by examining the URL as opposed to the IP address. You have content inspection. The device looks at some or all network packet content and determine if the packet should be allowed to pass. And malware inspection, a specialized form of content inspection that the device looks at packets content for signature signs of malware. Virtual private networks and remote access, right? So you have a lot of remote workers nowadays and working from home, and you set up these VPNs or tunnels from the home to the corporate headquarters or wherever the site is, and that way all the traffic is encrypted and safe and secure while they're accessing remotely. Major VPN technologies, you have point-to-point tunnel protocol, PPTP. It was once the predominant VPN protocol. For many years, almost all VPNs use the PPTP, and it is easy to set up on client computers because most operating systems included PPTP support. And we SSL, secure socket layer VPNs. SSL encrypts web communications, and many VPNs use SSL to provide encrypted communications. And users connect to an SSL protected web page and log in. Their web browser then downloads software that connects them to the VPN. And due to recent security issues, use TLS whenever possible, because TLS basically replaced SSL, but everybody just still calls it SSL. And this would be useful in a lot of cases for mobile devices, like mobile phones and that. If you want to get resources from the network, a lot of times you would use the SSL version of VPNs versus the IP protocol security or IPsec protocol for VPNs. This typically uses a client, a fat client, so usually you need a computer to set this up. And it's a suite of protocols designed to connect to sites securely, although some IPsec VPNs are available for end users. They often require the installation of third-party software on the user system and are not as popular because of that. Many organizations, though, use IPsec to connect one site to another securely over the internet, and the required IPsec VPN functionality is built into many routers and firewalls, allowing for easy configuration. As I said, the IPsec is going to be more your site-to-site, remote sites to corporate over the internet. If you don't want to spend the money for expensive private dedicated lines that avoid the internet, so you're going to use this IPsec to go over that. But the difference is with IPsec is you got the full feel. You're actually on the network and you can have full access to every application and everything that you would have normally in the office, whereas the SSL, you only have limited functionality and limited access to whatever could be put on the web page. For example, like Outlook, you can get full Outlook to load in IPsec, whereas SSL, you have to use the webmail version. Network Access Controller, NAC, enables you to add more security requirements before allowing a device to connect to your network. It performs authentication and posture checking. It follows the IEEE 802.1x standard. This is a lot of times organizations will have NAC devices. So when you bring your own device from home and you connect to the network, it will scan the device and make sure that you have a firewall, antivirus, etc. And if you don't meet some of the requirements, it will segment you off into a dummy network where you really only have access to be able to put antivirus or something on. You won't get full access. But if you pass all the checks and you've got all the security devices or applications and everything up to date and patches ran, it'll allow you access onto the network. Wireless networks deal with wireless access points, or WAPs, the connections between a wired and a wireless network. Fences don't stop wireless signals, and a lot of times walls don't either. You got to be very careful how far out your wireless network will reach out into the parking lots and that. Anyone with a radio within range of the wireless network can capture all data sent on that network if it's not encrypted. We have some security controls, so you can do VPN over wireless, and you can use wireless encryption. WEP is so insecure and flawed, you should never use WEP. Nowadays, you got WPA2, Wi-Fi Protected Access 2, and then you have a personal or enterprise, and the difference is authentication, having a server involved. If you have a server also doing authorization and authentication, you can do WPA2 enterprise, and you should be doing that in your organizations. But at home, WPA2 is the preferred method. Actually, WPA3 I think is out. But I haven't seen it on any my wireless access points yet. But I believe it is out. And then the SSID broadcast, you can actually turn that off. But when you go to look at the list of Wi-Fi to connect to. That's because it's broadcasting, but you can actually turn broadcasting off and have to know what the SSID is and enter it to be able to find it. Some devices can work with that, some don't work well with that either, so a lot of, your mileage may vary. And then you can even have MAC address filtering that only certain MAC addresses are able to connect to the wireless access point. But if you have more than 5 or 10 devices, this might become very hard to manage. And if you get a new device and your old device is broken and you only let one device have access, you'll have to reset everything to be able to get access. All right, so wireless security hardware. So you have different antenna types. Wireless device antennas can have a large impact on the device's area of coverage. Generally, external antennas can reach farther than internal antennas, and also antennas can transfer and receive in different ways. They can be omnidirectional, all directions, or semi-directional, limited direction, or high directional, focused direction. So you need to choose the right antenna for your organization's use. I used to have a wireless ISP, and my longest wireless link was just over 5 miles. So I did that off a 100-foot tower with a single omnidirectional antenna, and just not really that much different of what you would use at home access point. But I got over 5 miles just because of the antenna gain and the height of the antenna. Antenna types make a difference. And then antenna placements. You can select the best antenna for your device, and then you need to carefully place the antenna to provide coverage that you want and not for anyone else. Place an omnidirectional antenna near an external wall will likely make your wireless network available to people outside your building, so be careful. Power levels. You can change the power wireless device uses from the configuration settings. Lowering the power settings from the default will reduce the area the device covers, and this setting can be helpful when attempting to limit the visibility of your wireless networks. And also, more power doesn't necessarily make a better signal. You could actually end up causing problems, especially if there's a lot of interfering areas and you can get reflection, things like that. So power is not always the solution, but reducing the power when you can it isn't bad, and it will limit the area and also could give you a better signal within your local area that is covered due to bounce back and reflection and things like that. Captive portals. A captive portal is a web page that is displayed for all new connections, and your wireless device can redirect all traffic to the captive portal until the connection is authenticated. The most common use of a captive portal is to provide a login page for the wireless network, and if you're not logged in, you don't get full access to the network. And then you can do site surveys. One of the most important non-technical aspects of securing wireless networks is the site survey. Examine the physical area you want to serve with a wireless network. Facility floor plans can help determine the best placement for your devices, and then use diagrams to plan your wireless network before you physically place the device. And that is the end of our chapter. I will see you in chapter